Poznan University of Technology.
Okay, thank you, Professor Meklai and Professor Powell, for inviting me. It is my privilege to be here, and I really appreciate the honor of being able to address you. So I think without further ado, I will start with the lecture. And I thought uh, artificial intelligence has gained tremendous momentum in the last few years. You may have heard of ChatGPT, you may have heard of many other things, and almost a revolution is going on. So, uh, what I'm going to do is basically first, I want to define what do we mean by AI? What is AI? After I define what is AI, can you all see this? Yes? Okay, so I would talk about generative AI. So that means you may have heard of, you can generate the voices of individuals, you can generate images, videos. So what does it involve, and what is the technical use of it? I will go over a little bit history of AI, and then I will follow it up with some background information so that whatever we talk, it is in context. After that, I would define what do we mean by learning, because almost all AI systems learn. So what exactly do we mean by when we say a machine learns something? After I talk about learning, I'm going to talk a little bit about machine learning in general, and within machine learning, what is deep learning? Uh, and then within deep learning, I will talk about CNNs and RNNs, which are very relevant for example, time series prediction, for example, image generation, voice generation, and so on. Finally, I will talk about some reflections on where we are and what we think might be the future. And some use cases, I wanted to bring one or two things that we have done. Our research group at Syracuse has done, so I wanted to bring in some use cases of machine learning. I am a computer scientist by training and by profession. So all my life, this is what I have seen. But somehow my inclination is more towards something tangible, something that you can hold in hand. So you can say, okay, I cannot hold software in hand, but what I mean by tangible is something up. Whatever research we do, we should be able to build a product out of it. So that is something I think it's not necessarily United States. It's many major universities are very highly focused on systems. And that is why my inclination has been more towards algorithmic machine learning. And then I would build prototypes, but I would not build the actual products. So industry can take these prototypes, industry can take these algorithms, and then build products out of it. So what is AI? AI is the science and technology to simulate human intelligence by machines and computers. So remember that the word right now is human intelligence, but there is something called superintelligence also, which goes beyond human intelligence. But for right now, we will define AI or artificial intelligence as something which tries to simulate human intelligence. Examples are autonomous vehicles, crop analysis, drug discovery, medical diagnosis, generative AI tools. So within AI, you would find typically machine learning and rule-based learning and very classical artificial intelligence. So machine learning will then be involve deep learning, and rule-based learning will involve, for example, if you say k-means clustering, standard algorithms, support vector machines. All of these are classical machine learning. Then within AI, we would define what is a narrow AI or artificial narrow intelligence. So artificial narrow intelligence is something which is trained on specific tasks. A very good example is Apple's Siri, because it recognizes the voice and then takes the action, but it is not generic. We have Amazon's Alexa, IBM's Watson, and self-driving vehicles, because they are trained on specific problems. Then we have strong AI, which is artificial general intelligence, and forget this R. So artificial general intelligence and artificial superintelligence, they are two things within strong AI, but they are separate. So they aim for intelligence. When we talk of artificial general intelligence, it aims for intelligence equivalent to humans. It's self-aware, has consciousness, conscious ability to solve problems, and can plan for the future. So it can predict what is going to happen and take corrective action accordingly. ASI which is artificial superintelligence, it surpasses the human abilities. And it is mostly theoretical at this point of time. So we have not reached the stage where we are going beyond human intelligence as far as machines are concerned. But you will see a very good example of artificial superintelligence in a movie where you had a rogue computer assistant in 2001, and I think the movie was A Space Odyssey. So I thought, pictorially you will see that superintelligence is here, artificial strong AI, machine learning, rule-based systems. Then within machine learning, you will have narrow AI and superintelligence. So in a way, gives you a good Venn diagram of how intelligence is defined. So what is generative AI? A very good example my friend from Dartmouth gives is that if we train a machine to say move your finger like this, so that is the only task we have trained it on. And we train a separate system to move thumb. So it learns how to move thumb, it learns how to move finger. But if it can combine autonomously both of these together, there we have not trained it to pinch your hand, then that is a generative part of the AI. So only we have trained it this, but this part, looking at and pinching, is what is it? It is generative AI. So what it means is that another example would be that if it takes the work of Rembrandt, some paintings, and then it can generate similar paintings, which somebody will think has been painted by Rembrandt, but actually not by Rembrandt, but it is generative from the base samples. And we encode a simplified description of training data. Training data is Rembrandt's picture, and we will go over the transformative models and so on and how it is done, but very high level. So that kind of gives a description of generative AI. I will go over a little bit history. So I do teach a course on biometrics, authentication, which is my research area. And when we talk about biometrics, we say, okay, biometrics has not been there for 100 years. It has been there for time immemorial, because you can see the prints on stones and so on. But that is not the case with machine intelligence, because computers came very recently. So perhaps the first description of machine intelligence or how it was given by Alan Turing in 1950 in his book Computing Machinery and Intelligence, and he talked about can machine think. So there's a famous Turing test, and the Turing test is, I think most of you will be familiar with it, but I'll just very briefly describe that if you have a curtain and you have on the back side of it, you have a human and a machine, and on this side, somebody asks a question. And whatever the response, if the human sitting on this side cannot figure out whether it is the machine or the human who has answered, then it is the machine has intelligence. So that is rudimentary, but it has stood the test of time. Then in 1956, John McCarthy, he used the word artificial intelligence, and Noel Shah and Simon created the first running AI software program called Logic Theories. 1967, Mark Rosenblatt, he introduced Mark I and perceptrons and neural networks that learn. But Minsky and Papert from MIT gave arguments against it. So this is very interesting, and I'm going to stop here and go a little further. Next slide, because I want to explain why, what arguments did they give. And I think my PhD, I started in 1988. It makes me a little dated, but at that time, my professor in US said, look, not many people are working in this area, so let us start work on neural networks and image processing. So at that time, still, even at that time, people were thinking neural networks are not going anywhere. But it's something in 90s that it picked up. But let me go a little further, and I will come back to this slide. So somehow, can you see this line here, right? So I will give a very simple model of a neuron, a simple model of a human, so mathematically what you can do is that you can give it input x1 through xn or x1, x2, and you give it a wave, which is like two neurons connected together with a synaptic strength, that is W1. And you just multiply each of them and put a nonlinearity. Simple nonlinearity is if you choose a theta, if it is less than theta, then you make it 0. If it is greater than or equal to theta, then you make it 1. So this is just simple neuron. So that is a very simple model of neuron. Like if you take two inputs and one output and you multiply by neuron. I was told to keep it very simple, but I really felt like that I should introduce this. And so if you look at the gates, and electrical engineers use Boolean gates. So if you have 0, 0 input, the output is based on if you have an AND gate and you have an XOR gate. So if input is 0, 0, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1, and exclusive OR is 0, 0. So they have to be different, then they become 1. So now, if we take this gate and suppose we want to do an AND gate implementation. What you can do is that you can choose weight 0.5 and 0.5 and theta as 0.6, and this gate is implemented. This simple one neuron can implement the AND gate. So, and you can see that it becomes 0, 0, 0, so on. So you just implement 0, 0 multiplied by the weight, and you will get the output. If we want to look at it pictorially, the same thing, you will see the classes are 0, 0, and the output is 0. And so you have all three zeros by blue circles, and 1 is by yellow circle. So one can easily draw a decision boundary which will separate these two classes, 0 as one class and others as another class. So same thing pictorially you can represent here. What Minsky, the argument they gave, so remember this is only one neuron. If you look at human brain, that has about 10 raised to the power 12 neurons, massively parallel. But we are looking at very simple unit. So if you look at XOR, 0, 0, 1, 1, 0, there is no way you can draw a straight line that will put yellow in one class and blue in another class. You cannot draw it. So his argument was that neural networks are no good because if you take one neuron, it cannot solve an XOR problem. So this is something, now I'm going to go back. I think this is the argument he gave. Let me see if I have it. Yeah. So this is the argument Minsky and Papert from MIT gave, and they said, look, neural networks are not very powerful. But then later on, people said that you don't have to have one layer, you can have multiple layers, you can have 2 layers, 3 layers. People proved the theorem that if you have 3-layered neural networks, that you can solve any problem. So that was later on. Looking at hindsight, it looks very simple, but at that time when people were working on it, it looked, big thing, and especially if somebody like Minsky saying that they are no good, say almost everybody followed. So in 1980s, BP, backpropagation network, becomes widely used. In 1997, IBM developed Deep Blue, which beats the world chess champion Garry Kasparov. 2004, John McCarthy writes a paper, and what is artificial intelligence, and defines AI. So my definition very much follows John McCarthy's definition. 2011, IBM Watson beats champions Ken Jennings and Brad Rutter at Jeopardy! 2015, Baidu's Minwa supercomputer uses convolutional neural network to identify and categorize images which are better than average human. 2016, DeepMind's AlphaGo program uses deep neural networks and beats Lee Sedol, the world Go player. So after 4 moves in Go, there are 14.5 trillion moves. But the machine was able to beat Lee Sedol, who was the world Go player champion. 2023, 2024, right now, we are looking at rise in large language models such as ChatGPT and so on, and that is where the crux of my talk would be. So I think I already talked about this because I wanted to bring it in the context. So what the solution is, so this is a model. If we have one layer, this is a model of the perceptron. You have weights, W1, W2, Wn. You have inputs x1, x2, xn. Multiply it and put the output, but you have to backpropagate the error. The desired output is this, actual output is this, the difference will be error, and you update the weights based on that, and backpropagation is based on updation of weights, but you have multiple layers. So now you don't have one layer, you have multiple layers, and you can backpropagate the errors, and in a way, it is a model of the human brain. So now what you would see is massively billions of neurons, which are, for example, ChatGPT, Google, ChatGPT's generative models. They use almost same model, but there are massively large number of neurons which are interconnected with each other, and in a way, they represent the human brain. Okay, so this is something that we did. So if you have multiple inputs, now you can draw very complex decision boundaries. So you can separate them. So even if you have this class, even if it's a 2-class problem, then you can draw very complex lines because you are not looking at, when we looked at one neuron or when we looked at perceptron, we were looking at straight line. But when you have multiple layers, you get a polynomial of any degree. And somebody proved that if you have 3 layers, then you can have polynomial of n degree, very high degree. So in a way, you can separate any complex classes. So whether you have an image, this is my picture, or you have something like this, then you can get the decision surface of a circle. I think I'm going to pass this. And before that, my lecture was to continue like this, but my experience is that if we bring in a video, it kind of draws in the attention. So I thought this will be a right time, and I will come back to it, but this will be a right time to bring in some work that we did. Okay. Welcome to the Louisiana Tech University. Okay, so this is something that we did, and this does not use deep learning. It uses machine learning. It uses classical machine learning, and this is something we did in 2011, 2012. So that is how much? 10 years back. So this was something United States has a Defense Advanced Research Projects Agency called DARPA, which funds for cutting edge research. So 10 years back, it was very cutting edge. So we had funding. I was the PI, and I used to be directing a center at Louisiana Tech at that time. So anything that you see here is open to public. So it is nothing confidential. It has been approved for public dissemination. It is actually on YouTube as well. But all that you would see here is done by students. So whether it is voice, whether people you see are all students, my students. And I think all of them are PhD students. Actually, there are two of them. So it's about 6-7 minutes.
The demo is for our work on the active authentication of smartphone users based on how they execute touch gestures on the screen, how they type, and how they move while they hold the phone. The philosophy behind this kind of authentication is that users have a unique cognitive fingerprint of how they interact with technology, for example, how they use a smartphone in this case. By defining and extracting features that best model this cognitive fingerprint, we are able to non-intrusively authenticate users while they go about their activities on the phone. A part of our demo is about a new family of robotic attacks that we have designed to test these kinds of authentication systems. Our robots very closely mimic human swiping and are meant as a rigorous performance evaluation tool to motivate the design of active authentication systems that overcome the most sophisticated adversaries. Here, we present the swiping component of our active authentication system. The woman in the top left corner of the window is swiping on the touchscreen as she reads content on the phone. While she executes touch gestures on the screen, our system extracts features that model the different aspects of her swiping behavior and feeds them to the authentication module. The block on the right side shows some of these features as extracted from a single touch stroke on the screen. The model of the phone shows a geometric representation of the features for a single touch stroke. To the right of the phone, a more straightforward definition of the features is given. In the top left screen, the user is swiping on the phone while she reads. The active authentication application on the phone is operating in training mode, meaning that the user's swiping pattern is being stored as a reference template against which future authentication decisions will be made. In the top right screen, the same user later swipes on the phone during the testing stage. The graph in the bottom screen shows the match score between the user's swiping pattern and the template stored during training. The score is always above the yellow threshold line, showing that the user is successfully identified by the system. Another user in the top right screen is masquerading as the user in the top left screen whose template was stored earlier. The match score below the yellow line implies that the authentication system rejects the masquerading user. The second component of our system is authentication based on body movement patterns. The phone in the lady's hand captures her acceleration in the X, Y, and Z directions while she walks. From these acceleration readings, our system extracts a number of features, some of which are shown just below the video. The features undergo a number of processing steps, including, but not limited, to removing the gravity component, fixing the frame of reference, and removing of outliers. The video on the left demonstrates a scenario in which body movement data collected from a user is compared with data collected from the same user at a later time. The first floor plots on the right show the user's acceleration in the X, Y, and Z directions and the resultant of these accelerations. The lower plot shows the authentication score, which is high, that is, above the yellow threshold line most of the time, implying that the user is being positively identified by the system. In the bottom left screen, a different user masquerading as the original lady on whom training was performed is rejected by the system as seen from the authentication match score, which is always below the threshold line, We are currently carrying out tests on a larger population to evaluate the performance of this system. The last component of our authentication system is the typing module. Here, a user is composing an email while the system extracts features such as the key hold times and interkey latencies. The figure on the right shows an example of the features that our system extracts from a string such as ABC. We are currently working on the initial performance evaluation of this typing component of the system. As part of our research, we have also designed a set of robotic attacks that we envision to be the performance evaluation benchmark for these types of authentication systems.
Hello, my name is Now. How are you doing?
We demonstrate one of these attacks based on the humanoid Now robot. On the left, a human executes a touch stroke, which is sent via a local wireless network to the server, from where the robot reads it and executes an imitation of the stroke. Observe that the robotic stroke is very similar to the human-generated stroke. Now is not only matching the path, it is also closely matching raw features such as the time, distance, and starting and end points as seen from the graph. An adversary without access to an advanced Now robot can also design a similar attack using the much simpler LEGO EV3 robot. The EV3 robot on the screen uses 3 motors. One motor drives the robot along the breadth of the phone. A second motor drives the robot back and forth along the length of the phone, while the third motor moves the robot vertically on and off the screen. The object being used to touch the screen is a piece of Play-Doh attached to a AA battery. On the phone on the left, a human executes a stroke. On the bottom right of the screen, the LEGO robot makes 3 imitations of each human stroke. The graph in the top right screen shows how closely the various features extracted from the robotic stroke match those extracted from the human stroke. Observe that the LEGO strokes very closely match the human strokes. Our trimodal authentication mechanism combining typing, swiping, and body movements is one of the techniques we are using to overcome these kinds of attacks. In general, by combining these modalities, it becomes exceedingly difficult for attacks such as those due to robots to succeed. In addition, we are investigating liveness tests that can delineate between a human and a robot while not being intrusive. Thank you so much for your time and attention.
So this was a very representative example. We have added much more to it. We are also looking at emotion recognition and few other things. But however, most of our work is now focused on generative AI. So I thought this will kind of a little segue to put things in context, that what we have done in the past, which is about 10 years old, is using classical machine learning. It is not using generative AI. It is not that we have an image or we have a video, we have another video, we combine these video and create a new video, which is completely different than what somebody would have imagined. So what I'm going to do now is continue with slowly get into deep learning and generative AI and kind of wrap it up. So what you will see is that if deep learning is a part of machine learning and neural networks are part of machine learning but not necessarily deep learning, then what are the differences? So machine learning focuses on the development of algorithms that enable computers to learn from and make decisions based on data. Deep learning is a specialized subfield of machine learning that uses neural networks with many layers, hence the word deep, to model complex patterns. So you will see here that for machine learning, traditional machine learning algorithms use very simple neural networks, maybe 2 layers, 3 layers, 4 layers, and deep learning uses massive, very large amount of neurons. It has massive, large number of layers. In traditional classical machine learning, as you had seen even in the phone, we have to extract features, whether it is the length of the swipe, that is one feature, time it takes, the angles it makes, so on. These are features. We have to extract features. Whereas in deep learning, you just feed it the raw data. So if you have an image, you don't have to extract features. You feed the image itself, and it will extract the features from the image. Machine learning, for example, any classification algorithms, support vector machines, k-means algorithm, any distance-based classifiers are well suited for smaller data sets. If you have very small data sets, you don't have huge data sets to train, then you will use classical machine learning. But if you have large data sets, very, very large data sets, for example, you can extract essays from internet, Wikipedia, and so on. So you have huge data sets to train the model, then deep learning will be very, very suitable because it can generalize very, very easily. Within machine learning, classical algorithms are, you will have supervised learning and unsupervised learning. In supervised learning, you will give it an exemplar, and it learns that exemplar. In unsupervised learning, there is no exemplar. And I'll be happy to answer any questions as we talk, or even at the end of the lecture, because the audience is very small. In my class, there are 160 students. So especially in machine learning class, we have a large class, and I am open to questions at any time. Within supervised learning, you will have CNNs, convolutional neural networks, and I want to define convolutional neural networks, recurrent neural networks, and so on. And here is deep learning involves, and I forgot GANs, generative adversarial networks. I think it is DQN, and I'm forgetting the name, but all of these algorithms will fall within the domain of deep learning. So if we want to study deep learning, what areas, or if we want to study machine learning per se, and deep learning, what areas are needed? So typically you will involve all computational statistics, pattern analysis, neurocomputing, linear and nonlinear algebra, optimization, psychology. I have not put all of them, but these are the areas. Anybody from these areas can very easily get into machine learning. So when I was preparing, when Professor Pavel said that you need to come and give a talk, so I have a PhD student, very almost close to graduation, and I said, look, I have to give a talk. Can you make a figure? Because if I talk in straight letters, after some time I can lose the audience. So he said, okay, professor, what I can do is I can generate an image, but I don't need to generate an image. I will ask generative AI to generate an image. So he input these, and this is the image that I think it is ChatGPT which generated. And can you see, when I looked at it, and he did it right in front of me, I said, look, there are spelling mistakes there. It says composition statistics. So he said, professor, this I cannot change because this is something generated by the ChatGPT. It has taken this input and has a huge amount of database from which it has learned, and has the prompt, I think, was generate an image that represents these fields. And it generated somehow, but this would be a good example that even at this stage, it is not intelligent enough. It is still evolving. Maybe the data is not correct. And I said, okay, let me keep this and point it to the audience that I'm aware of these mistakes. Like do you see composition, right? So it actually should be correct, but it is a machine-generated image. It is not a human who has drawn the image. So how deep learning works? The underlying algorithm for deep learning is backpropagation, where you have a desired output at the end, and the output comes here. The error of that is backpropagated. You take the differentiation and change the weights. And changing of the weights or adjusting of the weights is what is called learning. You have a massive set of neurons, and it requires tremendous amount of resources, because if you have billion neurons to compute, you will require large number of GPUs. And that is why you will see NVIDIA and all that are growing so fast because of the deep learning and applications based on deep learning, whether it is images, whether it is voice, any of more modern applications. You will also need distributed cloud computing. And most of the times, the actual code that you would write is using PyTorch, TensorFlow, JAX. These are the software tools that we use. And I thought to put it here because you might use deep learning algorithms in your work as well. So I had debated to put this because it can become a little technical, and I didn't want to keep it so technical, but I thought this is core to deep learning, so I will give a very high-level description. There are basically 4 different types of deep learning models. One is CNNs, or convolutional neural networks. Second is recurrent neural networks, and they use backpropagation through time, and autoencoders and variational autoencoders, and generative adversarial networks, or GANs. So you'll see a typical picture of each of these. And convolutional neural networks will have various layers. And I think I have put a separate slide for each of them. It is used primarily in image processing and vision, and at least has 3 main types of layers: a convolutional layer, a pooling layer, and a fully connected layer. So these 3 layers. Convolutional layer working and reworking the original, it convolutes. And detailed patterns, you can discover detailed patterns from the convolutional layer. Earlier layers focus on simple features such as colors and edges in the images. And as the image data progresses through the layers of the CNN, it starts to recognize elements or shapes of the object until it finally identifies the object. So I put a very simple example. So if you have, for example, an image, so an image will be a matrix, right? If you have an image, if you have a 64 by 64 image, you will have a 64 by 64 matrix, and each pixel point will, if it's a black and white image, then it will be 0 to 255 value. But if it is a color image, then you will have RGB value. So it's basically an image. So if you have a 3 by 3 image and you have a kernel, very simple kernel, 1010, and the convolutional, what does it mean? You run this kernel on this, so you will have 1 multiplied by 2, 0 multiplied by 1, 0 multiplied by 1, 0 multiplied by 1, and you will get 2, right? So that way you convolute on the whole matrix. And this is what you will get. So that is so we have a 3 by 3 matrix as input. We apply a CNN layer with 2 by 2 kernel. Padding is 0 and stride length is 1. So you have only one shift. And you can make a very complex example, but this illustrates what we mean by convolution. In recurrent neural networks, they are typically used in natural language and speech recognition applications. By the way, I'm giving a very elementary definition so that the things are clear, but I'll be happy to go more detail if the audience wants it. So in recurrent neural networks, they are typically used in natural language and speech recognition applications as they use sequential or time series data. They take memory as they take information from series data memory as they take information from prior inputs. So recurrent is you have a network, one output is going there, but one of it goes back and becomes feedback loop. So you have a loop which is output, one part of output becomes another input. Autoencoders are where you take the input, and suppose your input is very large. Take an image of, say, 400 by 400. So that means 4 times 4 is 1600. So 16 and 4 zeros, which is a very large number. And if you want to process this, and you have a very small, you want to process it on a smartwatch, or you want to process the image on a phone. Phones still have more computational power, but say you want to process it on a smartwatch, you have a very small processor, you have a very small amount of memory, you cannot, very likely you cannot run a deep learning there. But you want to extract the features from the input. You want to extract the features from the image. So what you can do is that you can give all the 1600 input, 16, not 1600, 16 and 40, whatever that number is, 160,000 values. Take the same 160,000 values here, run a back propagation. So, and then when the weights stabilize, remove this. So now you have from 160,000 to maybe 20, 30 features. So it is taking that whole image and compressing it and putting it in about 20, 30 features, whichever one you choose. And there are various questions you can ask. How do we decide what is the number of this? What will be the optimal number? So there are rules of thumb that you start with a large number, then keep reducing and see how the accuracy is and so on. So there are very standard rules. But the general principle is that the input is the same as output, and you map very large amounts of data into compress it to a very small amount of data. And that becomes an input to your classifiers, your any other machine learning algorithms. So autoencoders are very active these days because many, especially for small devices, more specifically for if you see a ring, like smart ring would have very little memory. So you cannot do a lot of deep learning in very small devices. So there they become very active because you can take a huge amount and then compress it into very small and process that. So GANs have taken, I think in the last 4 or 5 years, they have increased in importance. They are consisting of 2 types. One is a generator, and second is a discriminator. Generator takes the value and generates an image, and discriminator separates it, whether it is the original image or a raw data. So you can take the original image, feed it, and use generator to generate more images from it. In the discriminator, it can take that same image and see whether it is the original image or it's a separate or fake image. So another model which has become very common or very standard is diffusion learning. And what happens in diffusion learning is you may have seen an application that you give to ChatGPT or any other, write an essay for, or pick any prompt. For example, write an essay that I have to travel to Poland and what will be the environment there, how, so on. So anything that prompt comes up. Now the system has to generate. So I will take the example of an image, and what the image process does is that you take an image and you add noise to it. And you add each time, you add a certain noise at each time step until it is completely unrecognizable. And then from that, as you are adding noise, you go back and remove the noise. And you will end up with an image which is very similar to it because you're adding random noise, which will be very different, but which will be in the same class. So if you have a dog image and you keep on adding noise and keep on adding noise, and you look at, generally you add Gaussian noise. And then we reverse the process. So this process is called diffusion when you're adding the noise, and when you take it back, that is a reverse diffusion. So you will have an image which is of dog, but which is not of the same dog. So for example, if you write an article and you want same concept, but somebody else has written. So you give this article to the system, it will add noise, keep on adding, and then when it comes to the reverse process, you will have an article which will have the same concept, but will appear as if somebody else has written that article. So transformer models are encoder and decoder, and encoder maps the input sequence to a continuous representation, and decoder generates the output sequence from the continuous representation provided by the encoder. So very simple concept, but again, for implementation, you will have direct code available. So I initially had to put the demo video here, but I thought it may be better to bring in here. So I want to give some example of the work that we did. And what we had used was that we wanted to find out whether cognition, how a person thinks, can differentiate, or can we identify an individual based on your thinking patterns. So, so the idea was that if we can have a device on the head, which is an FNIRS. It has 52 channels. So there are 52 channels, and it measures the electrical activity in the brain. And we gave these subjects, we placed the probe on the head of the subject. This was done in our lab. And we give them controlled rest for 20 seconds, then again rest for 20 seconds, then we give them an addition problem. And then we give them rest, and then we ask them to recite some phone numbers, give them rest, remove the probe, and this process we reviewed 4 times. So there are 3 tasks chosen based on review of psychological and neuroscience literature to produce consistent patterns of brain activation for the later identification or subjects. So the idea was that once we have recorded this, and later on we don't know who is who, and we put the same thing on the scalp, and then they do the application, then whether we can recognize or authenticate who that individual is. So we had 50 participants, 37 males, 13 females, and 4 identical sessions. And we newly placed the FNIRS cap on the subject at the beginning of each session, and probe centered on each participant's forehead. We actually had published these results in IEEE in 2015. Again, very recently we have something on emotion recognition, almost similarly, but we see whether the person, and we use transformer models, some of the models that I kind of browsed through. We use those models to recognize the emotions, but here you will see that the results, these are the 52 probes on the head. I wanted to draw a picture of the scalp, but it was becoming very difficult to draw the picture. So we just took a rectangle, and that kind of represents this part of the head. And I put eyes here, right eye, left eye, so basically like this. And then this part is what is on top. And you will see that the activation, these neurons are acting when the activity is going on. Addition, subtraction, sometimes these neurons are acting, these are the color map. And if we use classical machine learning, the mean EER, if we use all channels, then we have a mean EER of 0.043. Mean EER means equal error rate, means where false acceptance and false rejection become the same. So false acceptance of an individual claims who the person is, and the system rejects it, but is actually a genuine person. So that will be a false reject. False accept will be a person is not the person who claims, and then the system accepts it. So if that point at which these 2 errors become the same, if you do multiple experiments and you plot them at that point, so where they are, that is called EER. So that's a very good measure to compare the performance. So you will see that we have 0.043 EER for all channels if we use support vector machine, classical machine learning. If we use naive Bayes, we have 0.063. But if we choose the best channels, the error decreases. It becomes 0.036, and it becomes 0.046 in case of naive Bayes. And the reason I brought this paper is because exactly the same thing, but for emotions and for transformative model, for transformers, which I had, and diffusion models is what we are doing right now. I cannot share with you because the paper has been accepted but is not in press. But this gives a very good idea of where machine learning can be used for cognition. So it will be very much like that if you start thinking and somebody, you are on a Zoom call or you are on a phone call or you are very remotely and you are talking, but your voice is, you have impersonated. But the thinking you cannot impersonate. So I can really figure out whether you are you or you are somebody else based on the thinking patterns. Same thing on keystrokes. If somebody is typing remotely, based on the timing patterns, we can tell who that individual is. There is one thing you may have noted, that if this is the model of the scalp and these are the areas which are activated, this always remind me that when I was in elementary school and our teacher had a math problem. So if you go to him and he would always do like this. That means these are the areas of the brain which get activated when you are doing math, more calculation type things. So that brings us. So what I have done up to this point is I kind of defined what is AI. What are various different types of AI, what is classical AI, what is generative models. Then I did bring in some examples of what we have done, whether it was a DARPA project or whether it is a cognition project. And we defined very deliberately 4 different types of AI or generative AI. So where we are and what are the emerging trends and where we are going. So that means what is the past, what is the future, where we are going, and I have a few thoughts also which I will bring in some of the slides. Right now we are at a stage where we can translate varied languages. We can summarize a coherent text. You give a document to ChatGPT or Microsoft Copilot, and it can summarize it very well. For attorneys, lawyers, it can create briefs. It can do a lot of things. You can have very quick question answering sessions, seamless text generation. It classifies text. It recommends, it does sentiment analysis. You give it a text, you can say, is it a positive? Is it a negative? Are you angry? Is it friendly text? It's all it can do right now. It can do spell check, grammatical corrections, all this. What are emerging trends is that small languages models are emerging. Right now, most of the work is in English because the databases are in English. But smaller language-based models is where a lot of activity is going on. Regional languages, reasoning functions are emerging, and there's an economic revolution. So there's a good amount of funding and improved developer landscape. Almost every lab in the United States, at least, is shifting towards generative AI. If they are not in generative AI, it's very hard to survive because that is where everything is going. So where is future? So this is something that we discussed, I and my students discussed, and I have some ideas beyond that. I think it's very near future is personalized content generation and advanced conversational features, specific domain solutions. The thing that I wanted to bring in, and I'm going to come back to this if we have time, is actually, let me go back here. What I want to come back is that these are all machines. Whether we will reach singularity or not. So what is singularity? Can anybody say what is singularity? Right. So the machines become more powerful than the humans. And Ray Kurzweil and some futurists are saying that within 20 years we will be at a stage where the machines will be much more powerful than humans. So that's a subject matter of individual choice. And I think I did prepare a slide. I don't know, I took help of my student. Yeah, I think this is the slide I wanted to go to. But singularity is basically what you said, a hypothetical future where technology growth is out of control and irreversible. But that means it's an outcome of that, but you have the right definition. So that the machines are so more powerful than humans, and I think within 10, 20 years, because every time it is exponential. But if would they feel love? Would they feel hate? Would they have a feeling of guilt? Will they have, so if there is a war, if you have a super powerful machine and the weapons are made of these machines, will they just go and indiscriminately kill and conquer? Or will they say, okay, there are so many people who are suffering, so we should stop the war or we should do something? So these are some of the questions that I think, that means, will they have empathy? Will they have love? Will they have creativity? So you can, right now also you can say it can generate a poem, because what it is doing is, I gave you the example, you can do this, and it can combine these two, and it is based on these two learning, it can generate new things. It's very straightforward, because the core, how does it do it, is we have taken the model of neuron, and we have said that if you create multiple layers, it can do. And but even if it is electromechanical system, it's the same thing, because what you have is sensors and actuators. So the same signals go and actuators will make it move. So it's basically the brain is what we have talked about. So how do we create, or how do we define empathy in machines? How do machines really love? Do machines really create, or it is what we train them? So these are the questions. I don't have an answer. I think this is something that we need to look at. And so I think this was the definition which you gave, that machines become more intelligent than humans, and it will lead to singularity, which is a future where technology growth is out of control and irreversible. So eventually what you will see is that you have an convergence of various fields within 5 to 10 years, whether it is biology, whether economics, politics, geography, and I forgot what I wrote here, and I think that is applied sciences, and they will all converge through intelligent thinking machines, and something you will see. So you have a future where you are sitting here and you don't need physical strength, you don't need body, don't even need brain. The machines can do everything for you, and what you have is a future where you can transplant. You may have seen those movies where they transplant over that. I don't know whether that is achievable. It's very debatable. At the end of my class in machine learning, I always bring up these topics. In between is very technical, but this is always a controversial topic. And I think rather than going back, I would be more than happy to answer questions and then go back to the slides because, to keep the interest of the audience, I think it is much more relevant that if I follow from here on an interactive session. So thank you very much, and I think I will stop the lecture here.
Poznan University of Technology.